yeah, he isn't here today. Hold on.
Sorry, Greg.
We forgot. He'll enjoy it later. Okay, so the definition, page 105, it says, if there exists a non-zero integer m, so let's write that. That doesn't change. That did not work. Such that, and then it says a to the m equals e. So what do we use instead of a to the m? Well, I'm just saying, how do we write a to the m using addition? ma. So such that, make sure this isn't math, is m times a, but this is a added to itself, m times, equals to the, what is our additive identity? 0. I'm going to call that capital A. So we're going to let A be a ring and A be some element of capital A. Okay, so then that's our 0 element of our additive identity. So then it says, then the order of the element, the order of the element A is defined to be the least positive integer and with what property? Such that NA equals to 0. That's the order. So when we're talking about order now in our rings, we're talking about order under addition. The additive order. So I'm going to put down here, instead of just order, we'll write it additive order of the element A is defined to be the least positive integer n, so that NA is equal to 0. Now, theorem 1 in your book. Yeah, question. Yeah, n times a. It is, as long as you're talking about elements that are inside the group. N doesn't have to live in the ring. It's outside of the ring. So, you guys actually had to outline theorem 1. Let's go ahead and write the proof for theorem 1. Let's go ahead and type theorem 1 so I know what it says here. Okay, so what does theorem 1 say? All non-zero elements. Additive order. Okay, so we have to start with an integral domain. So let A be an integral domain. And we have to pick what kind of an element in A. A is not equal to the 0 element of our integral domain A. That's the additive identity. Now, notice what they do in the book. They start multiplying by some integer n. Why? Why do they say? You have an integral domain, right? It's an integral domain. What does it mean to be an integral domain?
There's no dividers of 0.
Yeah, no divisors of 0. If and only if for all A, B, and AB equals to 0 implies A equals to 0 or B equals to 0. Now this is multiplication in your integral domain, in your rate. So these could be elephants and pansies, we don't care. But they're inside the ring. They multiply together to give you 0. You don't like pansies? Okay, we'll go with roses. Thornless roses. Thornless roses.
I like garden roses. They're like giant pillows. No, I'm serious. They're big old suckers. Like this big.
That's true. That's true.
They're awesome. I've been looking at flowers from castles.
This would be the wedding thing.
I can school you guys on flowers.
And which ones are going to be in which bouquets, and yep.
My third one just starts asking, which one do you want in your boutonniere? I don't care.
I have to have a boutonniere?
What's it?
You say,
Yeah.
I have to have a boutonniere?
Wait, what's that?
There you go.
Pretty much I'm still trying to get a pocket square.
Okay, anyway, back to this. So, we want to multiply two elements together from our integral domain. That's the goal. So they do that by actually considering the addition of elements. And this is going to be for some n in the natural numbers. We're going to have NA, according to our definition now. What does this mean? A plus A plus,
A.
yeah, a whole bunch of A's.
Dot, dot, dot.
Wow, gotta
Plus
find the dot, dot, dots. There we go.
It's the
They're
third
hiding. There we go. Dot, dot, dot. Let's close that.
There you go. That's it.
Yeah. Oh, yeah. We can do the whole bracket underneath.
Let's make it a decoration.
Yeah.
Short handles of
Alt IC. C is decoration. And then you go get the stacked things, and I don't know what the shortcut is for that one. Oh, right there. And then below.
Let's do the butt one.
Oh, we got it below this time. So this is n times. But now, what is this equal to? A is equal to A times the identity element, right? So we can copy this down here and write it this way. Instead of just A, let's write it the identity element of A. And I'm typing the A with it. I know that's notation your book doesn't use, but I'm going to write that there. So we know it's not just one, the number one. It's the identity, multiplicative identity. That's where that comes from. That's the one in the proof in the book. That's actually the multiplicative identity. Yeah. No, they assumed, they said it like 3 chapters ago and assumed it ever since. And we forgot it. Trust me, we forgot it. Yeah. Well, it doesn't have to be a matrices, it's a matrix. And if we're talking elephants and zebras, it could be a giraffe. Yeah, or pansies. We're back on roses again. There we go. So then, do we have anything that we can factor out? Yeah, apply your distributive property n times. So we get the 1 plus, and how many times are we going to get that?
N times.
Yeah, n times. Oh. Come on. Here we go. Okay, you wanted this above, you said?
Then put the label below.
So Greg is gonna.
Look, you don't even have to write n times again. It already points to
Yeah. We better write it though.
He's like, I think the wrong data.
He's not here to go, oh, come on.
Yeah, it's okay.
Yeah, he is. He'll hear it.
I heard my name actually when I was class. She typed the integral sign. I was like, that would probably confuse Brody.
Oh, yes. We talk about everybody who misses class. Okay, so how many 1 sub a's do we have? N.
Oh, so it's
So N 1 a's, yes. Yeah, and if you want, we can keep this in parentheses so, you know, that looks better. And then, of course, all of that is times our A. But tell me about this N1A. N is not in our ring A, but the sums of the 1A's, which is what N times 1A means, is in the ring A. So that's in our ring A. Now, we would like to be able to talk about this equaling 0. Since A is an integral domain,
Wait, you said what is not an
N doesn't have to be an A. That guy right
A?
there
But
doesn't
N
have to.
times A's identity is an
Yes, because N times that is just the sum of them. And A is closed under addition. So that's in A. So don't think of that as N times it. Think of it as 1 sub A added together N times. Like reprogram the way we think.
A. Why in the book is that a little dot?
Because they're trying to get you to not think of it as just multiplication.
So both the same mathematics, but if we use our symbols slightly.
Yeah, exactly. So, I mean, I could put it as a dot there if you'd rather it be a dot.
No, that'll just confuse me more.
Okay, we'll leave it the way it is.
a lot of times.
Okay, A is an integral domain, so tell me about if this value right here equals to 0, then what can I conclude?
But N is 0. Or 0. A is 0.
Either the first one equals to 0.
Why don't we like develop a new notation system?
Oh, that'd be like having the Chinese alphabet.
Which is awesome.
This is probably true, but there's so many of them.
What is symbol between the two?
There's a spade. Let's use that. Use it.
We'll confuse Brody.
No, they're different symbols.
Oh, okay.
The next time Brody loses class, we'll just have different notations for We got a key up on the board.
Yeah, we really won't confuse you then.
So
Okay,
anytime
we'll
we're
confuse
talking-
me then.
Anytime we're talking with rings now, when it looks like multiplication, we're assuming this.
If it's numbers, if it's letters,
Okay.
we're assuming it's repetitive addition, repeated addition.
What's other than?
Except remember, you don't have, if you're talking about zebras, you're just adding zebras to zebras to zebras, so you don't have 3 in the set of zebras. So
Isn't it the same thing if you think of it as additive addition?
that's exactly in the integers.
So it's basically
So really, we're just gonna prove that now this is what we call multiplication when we're in the integers.
Yes, we're actually getting to the ring of integers.
Oh.
It's coming. We're not there yet. It's one of our last chapters. I don't think it's the last chapter, but it's one of the last chapters. So either the first one's equal to 0 or A is equal to 0. But what did we determine about A?
A is not equal.
Since A is not equal to 0, and I should put these as zeros of our...
Did we prove A not equal 0?
No,
just
we
said-
assumed it. We chose it to be that way. It follows that if our product is equal to 0, yeah, additive identity, then just say n times that, this right here, is equal to 0.
Well,
0 for A.
Yeah, the additive identity of A.
Isn't that
Not necessarily. Remember in our first set of rings we did in chapter 17, we had one that had an additive identity of like -2 plus. Yes, it was something strange. Depends on your addition. In matrices, the additive identity is a zero matrix. Yeah, you have addition, multiplication, but you can define those operations to be different things. Yeah. So now, go back and tell me, what is this value called if you have the additive identity added together so many times? Characteristic. Sorry, multiplicative identity. Yeah, characteristic. They defined, if you look on page 201 in your book, they have the characteristic.
Yeah, that really.
Those are 1 sub a's. Again, put your little sub a's on them. Those are the additive, the multiplicative identity of A. The multiplicative identity of A, 1 sub A. That's what the characteristic definition is.
Are we really adding them together? Okay.
Yeah.
We can believe these plus signs. So 0 sub A.
But it still seems like 1 plus 1 plus 1 plus
Oh.
1.
Yeah. So if this is n times, then the characteristic of A. Yeah. So the characteristic of A in this is going to be n.
So could you talk to a similar or analogous concept to order?
Sort of. It's the additive order of the multiplicative identity. Yeah, it's the additive order of the multiplicative identity, the characteristic. The characteristic is the additive order of the multiplicative identity.
If nothing else from this class, I can just say that and I'll feel high.
Today? Well, that's good. We can be done then, right? The additive order of the multiplicative identity. Think about Z2. It has just the elements 1 and 0 on it, right? What's 1 plus 1? 0. So the characteristic of Z2 is 2.
Oh, no. Now you go into this modular.
Yeah.
Take that example on the board.
Yeah, I like that example.
Do you think we should put it?
Or on there would be better.
I think Greg might want to see it.
Sorry, Greg. No, too bad. So is that the end of the proof?
We'll come back to it. We're getting interrupted. An example. Consider, actually we said Z2, let's make it a little bit different. Let's make it smaller than 29. How about 10? Consider Z10, that's our set 0, 1,
So the
2, 3.
would be 1.
Yeah. So when the multiplicative identity is 1, so we add 1 together.
And 10 times.
Yes. Why did I choose 10? How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is equal to 0 in Z10. Yeah. So what is a characteristic of Z10?
So what would be the characteristic of C? Oh, it's 0 because it said when it's infinite.
It's infinite, it's 0. Uh-huh. Yeah.
How would you do it if there was a set? Like, you know how they do they give you an
Has to be
expression
closed under addition.
such that, like, they give you an expression that's like such that this is underneath this. Like, cause like at the beginning of the majority of our latest homework problems, it's always like really easy, like integer stuff.
We're going to get to our homework problems for this chapter.
Okay.
Yeah, so we're going to get there in just a bit. I do want to go back and finish this one proof that we're looking at.
I'm waiting for the day to see raised to the loss and grades.
Yeah. Poor survey kids.
Times is 0.
Actually, we don't want to keep the poor set theory people in this class either. They'll go running away and never take a food class. They'll get lost. So go back to the previous one. What is that telling us? What are we trying to show? All the non-zero elements in an integral domain have the same additive order. What is the additive order here for this element? So we're saying we wanted to assume that this was equal to 0. So if it's equal to 0, A isn't what's equal to 0. It says the characteristic, the n of 1 sub A equals to 0. So n has to be a multiple of the characteristic. Does that make sense? Mm-hmm. Now, we just chose something that we added together and said assume it's equal to 0. So what would be the additive identity? It says it's the smallest positive integer, right? So let's go up and fix it. So we're going to say we want to look at, consider for some n in the naturals. Let's call this the additive order of n, and then I know it's the smallest value, right? Okay. N is the additive order of A. So that tells us that all of this has to be equal to 0 down here. We now understand what it means for it to be equal to 0. Since A is the integral domain, that tells us that n of A, I sub A equals to, 1 sub A equals to 0.
Is the 0 that you just typed also
Yeah, it's the additive. Additive identity of A. So right here, I know that this is the characteristic. Instead of a multiple, this is the characteristic. Why can I make that conclusion? It's the smallest positive integer. If there were a smaller positive integer equaling 0, it would come from this value right here. Okay? And so I'll say then n is a characteristic of A, for if not, then there exists a m in the naturals with m less than n such that m 1 sub A, the addition of 1 sub A added to itself m times would have to be equal to 0. Plug that back in and you get that A, MA, which is equal to, by the previous work, m of 1 sub A times A from our previous work is equal to 0, which is a contradiction of the order. Okay, that last part went a little fast. Let's look at it one more time. Over here, I'm claiming that n has to be the order, the characteristic. Because if it isn't the characteristic, then I can add 1 sub A to itself m times and get 0. And m is smaller than n. So then go through the previous work that we did up at the top, where we have all our a's added together m times. And then you multiply it by the 1 sub A, and then you factor the 1 sub A out, and you get to this step right here. You have m times 1 sub A, or m1 sub A's, times A. But this m1 sub A is equal to 0, and you have 0 times A, which is equal to 0, and all of these are 0 sub A. Which means that we have found a smaller value. That means that n isn't the order of A, like we assumed at the top. So since n is the order of A, we see that it's equal to the characteristic. So the additive order of an element is the same as the characteristic of your ring. The additive order of your element is the same as the characteristic of your ring. That make sense? Theorem 2, they just showed that the characteristic was a prime number. Similar type argument for that. What you need to really take away from what we just did right here, because we're going to look at your homework after this, is that when you have that m in front, m times a is not straight multiplication. It's a added together, m times. You can't just say m times a is in the ring means both a and m are in the ring. No. A is in the ring. A is added together m times, so it's in the ring. But m is just some integer. Does not have to be in the ring. That's what you need to have crystal clear in your mind to be able to do the homework. You guys understand that? Okay. Start working on the homework then from this section. I'm going to wander through and look at your notes.
So if you had like you could A represents a number and you could do 12 times A.
Yeah, it is 12 times.
12 times.
Yeah, exactly.
So the characteristic is the same as the additive order?
Yes.
But that's not the
Yes. Low battery?
probably so.
Now I see the, oh, I left my paper in the office.
Yeah.
Go get my
And
paper to record your.
it could be.
I'll be right back. Huh?
Danica, stop looking through all of her stuff.
Yes, sir. What is the number?
846.
Is that all?
Yeah. D1.
Oh, B1? C1.
D4.
Yeah, your A2, by the way, the proof is going to be very similar to what we did, but it's got numbers instead of all letters.
A4.
Yes, sorry, A4.
Is similar to what proof?
Similar to the one in the book from Theorem 1 that we just talked through. Very similar ideas. You should be able to figure that one out.